In this video, I'm going to briefly introduce us to the concepts of ontology and measurements in classical physics. And so we'll start here with ontology. And so ontology is a philosopher's term for what really exists. If you look it up, it'll probably say the study of being. And so by being, it just means, essentially what are we committed to saying actually exists. And so in philosophy, some popular topics in ontology, so things like, do natural objects exist? So natural objects are just like your sort of everyday objects, your coffee cup, your table, your window, your house, trees, things like that. Just stuff that, kind of we have noun words for. And so, do these things actually exist, or are they just sort of an object-wise collection of particles? So, you know, and this gets to, in philosophy, what's called nominalism, where, do we, like, so do tables exist, or are they just a table-wise collection of particles? So is table just sort of a word that refers to a table-wise collection of particles? Tables aren't a thing that we are sort of ontologically committed to existing. They're just sort of a shorthand for a collection of particles that are arranged in a certain way that then can sort of get used as a table. And so this is related to what's called mereological sums, where mereology is in philosophy sort of the study of collections of things. So maybe you've heard of things like the Sorites paradox, where you keep adding a grain of sand to an area. At what point does it go from being a pile or not a pile to being a pile of sand? So is there a single grain of sand which before it's added it's not a pile of sand, and after it's added it is a pile of sand? And so things like that. So another one is, do numbers exist? So I mean, it's pretty easy to say, like, if I have two things in front of me, then that is like an instance of two existing. But this is more in the kind of abstract sense. Do numbers, even that are not sort of instantiated by anything, do those numbers actually exist? Is there some sort of Platonic realm of forms where, abstract numbers exist in some way? And so if so, then in what way can they be said to exist? So another one is, do absences exist? So like a whole. So in what way can it be said that a whole exists when a whole is just a lack of something? And so other things that you see quite often in philosophy, so universals, which are, like you could think of, the universal tree. Is there like a sort of universal tree with which all other trees are sort of participating? Potentiality, which is like, you know there is this idea in philosophy that it's like, if you have your hand open and it has the potential to become a fist. So if you close your fingers, it becomes a fist. And so even while it's not in the form of a fist, it sort of has this potential to become a fist. Modality, which just has to do with necessity and possibility. Natural kinds, which are similar, I guess, somewhat to natural objects, but these are supposed to be like more concrete, like, something that has sort of necessary and sufficient conditions for being that thing. Social kinds, so those would be the kinds of things that show up in society, like different groups, different, like cultures and different sort of rules for interacting with people and stuff like that, or even things just like money would be a social kind. If there's no humans, then like a piece of paper that we would call money isn't money. It requires sort of a social network of minds in order for it to exist. Then we have abstract objects, which would include things like numbers and stuff like that. But anyway, uh, those are some popular ontological topics in philosophy. In physics, what we're interested in is what kinds of physical entities exist, or if we put this differently, how should the equations of physics be interpreted aside from the just shut up and calculate thing? Like if you know anything about Einstein's general relativity, maybe you've watched like the popular science things and they talk about sort of this fabric of space-time that gets bent when there's something massive there, like a trampoline when you put a bowling ball on it. But there's nothing in Einstein's field equations that demands you make that interpretation. And so are we committed to this idea that there's like a fabric of space-time? And so, if so, what kind of thing is this fabric of space-time? Another one, and this is the one we will be kind of talking about here. So do electric and magnetic fields exist, or are they just helpful mathematical tools for doing the calculations? We want to shut up and calculate, and so these fields are not something we have to say exist or don't exist. They're just something that are helpful to think about if we are trying to do the calculations. And so, this kind of goes to the debate between like Carnap and Quine about what you are committed to having in your ontology in a field of science and stuff like that. And so we also want to think about like what is the ontological status of something like an electrostatic potential or a magnetic vector potential, which is what one of the things that we're going to be talking about here, because this is one of those things that, well, I'll get into that after I sort of describe what it is. And so the magnetic vector potential comes from the fact that, so from Gauss's law of magnetism, we have the divergence of the magnetic field is equal to zero. Since the curl of a divergence is always zero, then we know that that this right here can be equal to the curl of this this vector potential is what they call it. So this A here is the vector potential. And just to make sure we're kind of on the same page, the curl is just sort of measuring this. So it's measuring sort of how much of like a loop you are forming here. So how tight the loop is on there. And so the curl of a divergence is always zero because a divergence is always something that radiates outwards. So radiates outwards in all directions. And so there's not going to be any kind of curl from that. So it will always be zero. And so since the divergence of this curl is zero, then for any vector field A, this means that we can rewrite Faraday's law, which is the curl of this E, so as the curl of this being equal to zero, because we have this being equal to this, we just add this to both sides and set it equal to zero. So the curl of that is zero. And since the curl of a gradient is always zero, so the curl of a gradient where phi is some scalar potential, so a scalar potential being something like, air temperature or air pressure or things like that, would be included in what a scalar potential is. So it's a magnitude but not a direction. So we can use the following. And so this negative sign is by convention. So we have the curl of this, and we have the curl of this gradient, which is also equal to zero. So both of these things are equal to zero, so we can set them equal to each other. Well, then we could just remove this this curl part of it, and now we have this electric field plus this change in this this vector potential being equal to the negative gradient of this scalar potential here. And so when we do this, so now we can subtract this from both sides and we end up with this. Again, just so we're on the same page, a gradient is, so we have this scalar potential here, which is just the function x squared minus y squared. You take the gradient of that and it just shows you sort of where it is growing. So the arrows are sort of pointing in the direction that the function is increasing. So it's actually turning this scalar field into a vector field here. So this is just the electric field in terms of the scalar potential and the vector potential. And so for Ampere's law and Faraday's law, we can get the entire laws here in terms of these scalar and vector potentials. So we have the Ampere's law and the Faraday's law here, both in terms of just the scalar and vector potentials. And so what these potentials do, so, so far this has just been kind of a fun little mathematical curiosity, but what it does is give us freedom to make some changes that ultimately make the math easier to work with in different cases. So for instance, we have our magnetic field being the curl of this vector potential. So we can change the vector potential by the gradient of an arbitrary scalar function without affecting B. So we can take our vector potential here and then add the gradient of some scalar function here. And that's because if we take the curl of this, then it's the magnetic field plus the curl of this gradient, which is always 0. But if we do change this, make this change to this vector potential, this will also change the electric field unless we also make the following change, which is just adding this time derivative of that function there, or I guess subtracting it from this this scalar potential here. So if we do both this and this, it will leave the magnetic and electric fields unaffected. And so these are known as gauge transformations. And so there are equivalent classes of potentials. So these scalar potentials here of all the possible scalar functions lambda that give the same field configurations. So that will sort of give the same magnetic and electric field configurations. So we're free to choose a particular set of potentials that make the terms in these in the above blue boxed equations up here disappear. For instance, in the Lorentz gauge, which we're saying we have to have that the divergence of the vector potential plus this 1 over c squared times the time derivative of this scalar potential being equal to 0 will make the blue box equations from above put into these simpler forms here. Where we can see as well that the effects of charges on these potentials propagates at the speed of light. However, if we do the Coulomb gauge, which says that the divergence of the vector potential has to be equal to 0, then those blue box equations from above will be these two equations right here. And what's interesting here is that this one is exactly the same as this one, except it's missing this middle term here because this c squared is essentially being set at infinity. And so we're saying that the speed of light is infinity, so it cancels out that term there, and so we are just left with this. And so this means that the phi in the Coulomb gauge is non-local. So it changes instantaneously without any speed of light delay. Yet both of these gauges will allow us to make correct predictions for electrodynamic phenomena. And what that means is that we're left with a question: what's the ontological status of this vector potential and this scalar potential? So it may seem like they're just some mathematical tools. They make some of the calculations easier. So you sort of want to choose your gauge based on what kind of calculation you want to do. But things like the Aharonov-Bohm effect suggest that these things are real. And I mean, this is controversial. There's still a lot of papers coming out even to this day where people try to show that this Aharonov-Bohm effect can be described without recourse to these potentials here. But what it is essentially is you do a double slit experiment. You have a solenoid here that's long enough that outside the solenoid, where these electrons here are going to pass around it, is going to be the magnetic field is going to be zero there, but we would still have this vector potential A right here. And what they see is that it does actually the shift the pattern of the electrons hitting your detector because it's creating this phase shift. So the vector potential is itself actually causing a phase shift in these electrons, which sort of suggests that it might actually be something real and not just a mathematical tool. And I go through this in a bit more detail in my playlist on quantum mechanics, where I actually look at all the different calculations and math and stuff. These sort of, I guess you could call it the shut up and calculate playlist, um, but the interpretation here is essentially, or at least the interpretation that is sort of the canonical one, is that this vector potential is something real, and it's something that's actually that you can actually measure. You can actually measure it by performing this experiment here. And so, I mean, this image that I got here is actually from a paper here where they want to just try to explain it with classical electromagnetic theory. But like I said, sort of the canonical interpretation of it is that this vector potential is something real. And so we will run into the same kind of question when discussing the wave function of quantum systems. So is it's this probability wave something real? And, if it is, then what does that mean that it's actually real? All right, so I also wanted to briefly discuss measurements in classical physics. So a measurement in Newtonian physics is you just go look and see if the particle or some macroscopic assemblage of particles, like a ball or something, is where the theory predicts it would be. And so we can use the kinematic equations here. I'm not going to go through these, but these are the kinematic equations if you take a freshman level physics class, at least the first semester of it. You're going to be using these quite a bit, as well as this F equals ma. But these give predictions, at least if you make some assumptions, like you're in a vacuum and things like that. But they make fairly accurate predictions for just things like throwing a ball, or the way gravity works, or the acceleration of objects and things like that. And so for that, you could just use sort of a ruler or a stopwatch to make a lot of these predictions. And in fact, if you take a freshman level physics class, those are probably the things that you're going to be using in the lab section for that class: rulers and stopwatches. But of course, these measurements can be done with sort of greater and greater sophistication. You can start getting, much more complex and expensive equipment to make different kinds of measurements. Uh, so yeah, like I was saying, in kinematics and dynamics, so dynamics being the application of sort of Newton's equations, you could throw a ball up in the air next to a measuring stick and get its height and time how long it's aloft with a stopwatch, and then just plug those things into these equations, usually using Earth's or not magnetic, but gravitational pull for the acceleration on these. But anyway, so in electrodynamics, if you want to measure the strength of an electric field, for instance, you need a particle with a known mass and charge. And so then you can obtain the force by just putting in the mass and charge here, measure the acceleration, and then you get your electric field. So to measure the acceleration, you could just use another ruler, or maybe something a little more sophisticated, but that does essentially the same thing as a ruler and a stopwatch, and just calculate the acceleration. And so in science, measurement is extremely important. So if your theory doesn't make any predictions that can be measured, then in science it's a worthless theory. I mean, like I said, it's in science. If you're coming up with predictions that can't be measured, then it's not really a good scientific theory. You know, it might be something like a good philosophical or theological theory or something like that. But in science, you need measurements. So if there are things in the theory that cannot be measured, then they must at least have some interaction with things that can be measured. So you want to be able to indirectly measure things. And so in these videos here, in a lot of, sort of foundations of quantum mechanics and philosophy of science and stuff, we often talk about a sort of generic measuring device that simply just consists of a probe and a pointer, where the probe here is what sort of interacts with the system that you're interested in measuring, and the pointer just indicates the value of the measurement. So, if you want to measure the charge of a particle, for instance, you put the probe in, you touch the particle with the probe, and the pointer here will give some output saying what the charge is. And so we can think of, this is just sort of a black box here. So when we are sort of talking about this generic measuring device, it doesn't matter how it actually works, because we want it to just sort of encompass any kind of measurement device that you could think of when you are testing physical theories. And so all that matters is that in a measuring device, what you're going to have is some kind of probe, something that will interact with the system in question, and then a pointer or a readout that tells you sort of the the parameters, sort of the outputs, the quantification that you are interested in for that system. And so this kind of thing right here is what we are talking about when we sort of talk about a measurement. But as we'll see in future videos, this idea of a measurement isn't as straightforward as this classical view of measurement would have you think. As we'll see in quantum mechanics, there is actually something called the measurement problem, and that's because, especially when you get to the quantum mechanical level of things, this idea of a measurement sort of starts breaking down a little bit. But anyway, I don't want to ramble on too long. That was everything I wanted to discuss in this video. I hope you found it interesting, and I will see you in the next one.